So we're going to talk about just the nature of forces. We know forces cause acceleration. Intuitively, you can think of a force as like a push or a pull. So like here, I'm going to push this, that's causing it to move. Simple enough idea. But, like what actually are forces? And that's actually a difficult question. And it turns out there are 4 known forces in the entire universe. I'm going to list those. I kind of list them in a certain order. All right, so we've got the force of gravity, the weak nuclear force, the electromagnetic force, and the strong nuclear force. And that's it. All forces are, these 4, at least as far as we know. It's possible there's other forces that we do not know about, but so far, this is it. And gravity, of course, was known a very long time ago. Gravity is the most obvious force. It's always present. You want to lift something, well, it's gravity's pulling it back down. Electromagnetic. Electric forces were known even in ancient times, although they probably weren't aware just how significant they are. But if you take something like amber and rub it with fur, they notice that like small particles will cling to it. A good example, although they didn't have this in ancient times, would be like styrofoam or something, like little beads of styrofoam. You can imagine rub this amber or like rub plastic with something, stick it in the styrofoam, and the styrofoam is going to cling to it. That's electric forces. Magnetism was also known in ancient times. They discovered certain rocks like lodestone. They would always point north. And so, and it turns out the electric and magnetic force are just different aspects of the same thing. So it's called the electromagnetic force. Now, out of these, it seems like gravity is the most significant. However, I put them in this order because this is going from weakest to strongest. Gravity is an unbelievably weak force, which is kind of surprising because it seems like it's a very significant one. But the thing about gravity is that one is like all matter attracts all other matter. So if you have 2 objects, they're just going to be attracted to each other by their mass. That's what gravity is. And as far as gravity is concerned, there's only one type of mass. We can compare that to the electric forces, where electric forces are based on a property called electric charge, and there's 2 types of charges, which we call positive and negative. This positive and negative labeling, it was Ben Franklin that came up with this. And so we have 2 different types of electric charges, and opposite charges like this attract each other, where if you have like charges, like if you have 2 positive charges, they're going to repel each other. If you have 2 negative charges, they're going to attract each other. And if you have getting mixed up here. If you have 2 negative charges, they're going to repel each other as well. But positive and negative charges are going to be attracted to each other. And so electromagnetic forces are actually extremely strong, but they're not very noticeable. And the reason why is because of this attraction between positive and negative charges, they tend to clump together. Like you always find positive and negative charges paired up. So let's say you put another positive charge nearby. So this charge is going to be repelled from this one, but attracted to this one. And so overall, the effect is going to be very small. It's not going to be really noticeable. because it's both attracted and repelled from the same object. So when you have these two charges kind of stuck together, which they almost always do. But that doesn't happen with gravity. Gravity is just based on matter, just mass, and there's only one type. I guess there's some theories about a possibility of negative mass, but no idea if any of that's real. So as far as we know, there's just one type of mass, and so because the effect is very small, but if you accumulate a lot of matter, that can turn into a very significant force. And then there's nuclear forces. These we don't really talk about in this class. They relate to what's going on inside an atom. Now, if you look at the electromagnetic force, for instance, if you look at, say you have the nucleus of an atom, you may know the nucleus consists of protons. There's also neutrons in there. But you have these protons that are all crammed into this incredibly tiny area. A good analogy would be like, say you have a football stadium, and you place a football in the middle. That'd be like the nucleus, where like say that the football stadium overall was the size of the atom, the football itself would be the size of the nucleus. So atoms are incredibly small, and the nucleus of an atom is even small compared to an atom, and we're cramming all these positive charges in there with no negative charges to balance it out. And so you can imagine there's an enormous amount of repulsion between the charges inside the nucleus. And there's a force, something's got to be holding that together, and that's the strong nuclear force. So this is the strongest force, but it's an extremely short-ranged force. So it acts between nuclear particles, like protons and neutrons, but if you separate them by even something as small as the nucleus of an atom, the force will, be insignificant. So it's an extremely strong, but extremely short-ranged force. The weak nuclear force, that's involved in certain types of radioactive decay. We don't have to concern ourselves with that. But as far as we know, this is it. These are called the fundamental forces. These are just part of our universe. Now, we're going to talk about gravity. That's the only fundamental force we're really going to talk about in this class. Electromagnetism is what you do in 122. So, but most of the forces that we deal with are electromagnetic in nature. And the reason why is, say that we have two atoms. Say we have an atom with a positively charged nucleus, and it's surrounded by negatively charged electrons. So the electrons are negative, and overall, there's not going to be too much of a force between these atoms because they're electrically neutral. Let's just say they are. Not all atoms are always electrically neutral. You can remove an electron or something or give it an extra one. Let's just say we have two neutral atoms. So the net charge is 0. And so you might think there's going to be no force between them. That's not entirely true though, because the electromagnetic force also depends on distance. But so there'll be very small forces. Like for example, let's say we have an electron right here. Maybe it's more repelled from the electrons than it's attracted to the positively charged nucleus, just because of distance. It's actually not that simple, but yeah, there can be small forces between them. But if you move these atoms closer together, these electrons are going to start overlapping with each other, and there will be a very strong repulsion. And since all matter is made out of atoms, if you try to cram objects together, if you push on the wall, it's going to push back. That is an electrical force in nature. So I'm pushing on this board, the board is pushing back. That is electrical in nature. Now, that's at a fundamental level. But gravity is the only force that we're going to actually deal with at a fundamental level in this class. And the force of gravity that we're going to use was discovered by Isaac Newton. And yeah, I think it was the same book where he published his laws of motion. He also discussed gravity. And I'm going to write down Newton's law of gravity. Well, here, let's kind of build it up in pieces. Let's say we have two masses, M1 and M2. Now, the force between them, they're attracting each other. That's how gravity works. Like M1 wants to move this way, M2 wants to move this way. And yeah, the force depends on how much mass there is. However, interestingly, it doesn't really care where the mass is. So let me give you an example. Let's say M1 is 4 kilograms, and M2 is 1 kilogram. There's going to be a certain force between these two masses. Now, if you look at another case, where say like M1 is 2 kilograms and M2 is 2 kilograms, the force between these two objects is going to be the same as the force between these two. And so like the total gravitational force depends on the product of the masses. Here, 4 times 1, 4 kilograms squared. You multiply these two masses, you also get 4 kilograms squared. So it doesn't matter which one is more mass or whatever. The force, we say the force is proportional to the product of the masses. So M1 times M2. And it also depends on the distance between the masses. Let's call that R. And the force is inversely proportional. So that means that would be in the denominator. And it's inversely proportional to the distance squared. So what that means is if you, say you have these two objects 1 meter apart, there's going to be a certain force between them. What if you increase this distance to 2 meters? Same objects, but now there's 2 meters. The force is going to be reduced by a factor of 4. So I'd say this is, I'll make it nice numbers here. Let's say this was 8 newtons. If you double the distance, we divide by 4, the force would drop down to 2 newtons. And if you triple the distance, or to draw this on the scale that I kind of picked here. So let's say we have 3 meters. The force would go down by a factor of 9. That'd be, 3 squared. And so this would be 8 over 9, or like 0.89 newtons. So this is called the inverse square law. Inverse because it's the bottom, and square because we're squaring the distance. Now, how did Newton figure this out? You might think he did experiments, just measuring forces. You can imagine, okay, let's just take these masses, measure the force, increase the distance, do it again, and discover this law, but that would never work. The reason why is these forces are so small. It would be extremely difficult, like Newton would have had no way of actually measuring these forces. But what Newton did, kind of historically, very important, back in the ancient times, we can't go too far back though. Let's go back to Aristotle. We had the Earth in the center of the universe, and everything orbits around the Earth. And again, that's kind of obvious the way things are. Go outside and look at the sky. Sky moves across. Clearly, we're not the ones moving, it's the sky. So again, that was kind of how things were for many hundreds of years, over 1,000 years actually. Now, if you go back to even ancient times, like the ancient Greeks had all sorts of ideas about how the solar system worked. And there was a guy named Aristarchus who said that the sun was the center and everything moved around the sun. Now, he didn't get too much attention, but then like around, at least since the time of Aristotle, this idea was fixed, and it became dangerous to question this. If you question this, you could literally get burned at the stake. Galileo was arrested for questioning this idea, and he was placed on trial, but he knew the Pope, and so instead of being burnt at the stake, he was just placed under house arrest. But not everyone was so lucky. But then along comes a guy named Copernicus, who actually said, this ancient Greek guy talked about the sun being the center of everything, and everything, including the Earth, is orbiting around the sun. And he knew it was very dangerous to talk about that. And so he decided it's maybe time to revisit this idea. He was very smart about how he did that, though. He wrote a book saying, okay, we all know that the Earth is the center of the universe, but when it comes to just calculating where things are in the sky, even though we know that the Earth is a center, sometimes it's helpful to think of the sun being the center and everything orbiting around that. So he was actually saying that the sun was the center of the solar system. They didn't call it that at the time, but just the universe as they knew it. But, he was doing it in a way where he was not really challenging the authorities on this issue, and so he got away with it. And then when he was much older and kind of near death, he wrote another book where he just didn't care anymore, because what are they going to do? He's old and dying anyways. But yeah, Copernicus kind of revisited this idea that the sun was the center. And everything orbits around the sun. So like the ancients knew about many of the planets. So we've got Mercury, Venus, Earth, Mars, and they also knew about Jupiter and Saturn, and that's it. So those were the planets that existed. I guess we'll continue. This is not exactly the scale, but we have Jupiter and Saturn. And the ancients, and even before Newton, knew this picture of the solar system, like by Galileo's time. They not only knew that the sun was in the center, but they knew the correct position of the planets, like which ones were closest and which ones were farther away. And they also knew how long it took for a planet to complete an orbit around the sun. Just by observations, it's called like the period of a planet. Like for Earth, that would be 1 year. But they knew like how long each planet took to orbit. And that's kind of all they knew about the planets. And there was this great astronomer named Tycho Brahe. I don't know if I'm pronouncing his name right, but he was one of the greatest astronomers of all time, particularly in the days before telescopes. He never had a telescope. They weren't invented yet. But he spent his whole life working at this observatory, just taking extremely accurate measurements of the positions of things like planets and the sun and the moon, and collecting all this data. And then when he died, he handed this over to his student, a guy named Kepler. And what Kepler did, Kepler was an astronomer, but he was also a great mathematician. And Kepler came up with his 3 laws of planetary motion. Now, if you ask a historian of science, they'll tell you Kepler came up with 4 laws of planetary motion, except one of those is complete nonsense, so we don't talk about that. But he had 3 laws that were very accurate. One of them was something troubling. What Kepler did is he wanted to prove this model of the solar system, that the sun was in the center, because that was still being debated. People like Galileo were very convinced that this was the correct picture, but he wanted to settle it once and for all based on observations. And so he considered these orbits as circling around the sun, and he could almost do it. He could almost make all the data that Tycho had collected he could almost do it and say that that fit perfectly into this circular orbit around the sun, except it wasn't perfect. There were some planets where the data just said they're not actually orbiting in circles. And so that kind of concerned him. Maybe this model's wrong. And so he decided to make this radical change. Instead of circular orbits, he said, what if the planetary orbits are elliptical, and then the data match perfectly? And that was a really big deal. Very controversial to suggest that planets moved in elliptical orbits, because everyone knows a circle is a perfect shape and an ellipse is just nonsense. But that's what the data said. And so Kepler said planetary orbits are elliptical. And he had a few other laws that we'll talk about later. One of them, he was able to relate the distance of a planet from the sun to how long its orbit took. And but anyways, these were very just descriptive laws. He's saying we look at the planets and this is what they're doing. As far as why they're doing it, who knows? That's just what's happening. And what Newton wanted to do is give an understanding of why the solar system acted that way. And so Newton started with Kepler's laws just as like an observational fact. And with Kepler's laws and his laws of motion, he was able to prove that only an inverse square law would give us the orbits that we're seeing. And so Newton, kind of, with his laws of motion and his theory of gravity, he was able to explain why things like planetary orbits. And that was one of his great accomplishments. So, let's get back to gravity. We can combine what we said earlier. The force is proportional to the product of the masses and divided by the distance squared. So again, we're dealing with very small forces, very difficult to work with directly, like with experiments, but ultimately came from observational, like astronomical observations. Now, this symbol means proportional to. In order to turn this into an equation, first we just write an equal sign here, and then we introduce a constant. And this is called big G. So remember earlier I called the acceleration due to gravity little g? Yeah, just because there's also another g, which we call big G. And that's what allows us to turn this relation into an equation. Now, what is the value of G? I'm going to write that down. All right, so big G, that is 6.67 times 10 to the minus 11. And the basic SI units would be Newton meters squared over kilogram squared. And so that is our theory of gravity. And again, this was due to Newton in 1666. And this lasted until 1915 when it was replaced by Einstein's theory of relativity. So there's actually two theories of relativity. He first came up with what we now call the special theory of relativity. And when he came up with that, he realized that Newton's theory of gravity actually had to be wrong, and he fixed it by what's then called the general theory of relativity. But again, that's way beyond what we're going to be doing in this class. So, and again, in most cases, Newton's laws of gravity work just fine. So, now that raises a question. First off, how do we know G has this particular value? And second, why does it have that particular value? And the first question, how do we know? We measured it. That's all we know. We measured the value of G experimentally, and that is the answer. That was actually done with a direct measurement. where this guy named Cavendish actually was able to measure gravitational forces between some very large objects. He did this amazing experiment. I'll see if I can find a link to it. It's worth reading because it's really amazing. He had this room where he set up the experiment. And this was still in the 1600s, I believe, that he did this experiment, although I'd have to double check that number. But he wanted, so again, think of the technology that existed in the 1600s. And he didn't want to be in the room while the experiment was happening because he knew that just by walking around, he could create air currents. And so, I mean, he was so precise in this experiment. So he rigged up these contraptions so he could control things from outside. And to avoid being in the room, it's like he took everything into account and did this really incredible experiment. Like one of the most impressive possibly in like the history of science. I read an article that was very interesting. I'll see if I can find a link that's actually free where you can read it. And then I'll post that if you want to read it. But again, why G has this value, nobody knows. So if you ever figure it out, there's a Nobel Prize, I'm sure. It'd be nice to know. So this is something, we don't know why, but that's the value it has. Okay, so that's Newton's force of gravity. Now, let's look at how we would apply this now. It looks like a complicated thing, and gravity always exists. Like, say I want to know the force on this object, you might think this is going to be almost a hopeless task. Because, there's the Earth, but, I'm in a room, there's a ceiling here. The ceiling is pulling upwards. If there's a tree over there, the tree's pulling it that way. It's being acted on by matter, which is all around us. But, the good news is that gravity is an extremely weak force. There's also kind of an additional problem you might see with using this law of gravity. And I drew it, like, say we have two objects, M1 and M2, that are separated by a distance r. But what if we have objects look like this, say M1 and M2? To say that they each have a certain mass is fine, but what about the distance between them? How could you even define r in this case? Where you've got, you can pick like the closest distance between any 2 points on them, or what about like you can imagine just connecting, you could have significantly different r's connecting these two objects. And so this law only applies to what we call point particles, which are objects that are very small compared to the distance separating them. However, Newton was able to prove that it applies to one other case, and that is if we have a spherical object. So if we have a spherical object, and say another object outside of it, we can make this spherical, let's say that this is a small mass m, and the spherical object is very large, it has a mass m, and again, this mass is distributed all around the sphere, but what Newton proved is you can treat it as if all of the mass was concentrated at the center of the sphere. And then we can define r as the center to center distance, and then we're good. And the good thing is this works in almost all cases because gravity is only significant for large objects, and large objects tend to be spherical, like planets and stars. They have to be spherical because they're so big, they have so much gravity that, like if you had an object that wasn't spherical, like say you had a planet that was not spherical, it would become spherical over time. Like if you had a planet that somehow looked like this, like say this is like a mountain here, mountains break apart, things tumble downhill. I mean, over time, this planet would be, would assume a roughly spherical shape. Now, are planets actually spherical? No. mainly because they rotate, and that causes them to bulge at the equator. But for our purposes, planets and stars are spherical. If you work for NASA, you're going to have to take into account that the Earth is not a perfect sphere. But that's if you work for NASA. For this class, we're going to be fine just treating planets as spherical objects. So let's say this spherical object is Earth. And this has a mass of around 6 times 10 to the 24th power kilograms. Okay, and r is the distance from the center of Earth to this mass. So, we know the radius of the Earth. That's around 6.4 times 10 to the 6th power meters. So let's say that this smaller mass is, say, this eraser. So if I want to know the force of gravity on the eraser, it looks like I'm going to have to do this. I'm going to have to know this constant g, the mass of the Earth, and the radius of the Earth. And what if this eraser isn't exactly on the ground, like I'm holding it above the ground? Let's say I'm holding it a height h above the ground. You know, we'd have to take that into account. And this looks like a very unfortunate situation because, you know, force of gravity is always acting on everything. And so if I want to describe, like, say, this object just resting on the ground, well, I need to know all the forces acting on this object. Or let's say we put wheels on it and, you know, push it. So it starts rolling. And we know from Newton's second law, F net equals ma. So in order to use Newton's law, the net force is just the sum of all the forces acting on an object, and gravity is always one of those. And so it looks like anytime we use Newton's laws, we're going to have to do all this. We're going to have to know this and this and this, and also the height above the ground. Yeah, I'm going to separate. This is our E, radius of the Earth, and then that's the height above the ground. And again, that would be R overall. However, we're not going to have to do this. It turns out this is going to be very easy for a couple of reasons. For one, let's look at the height above the ground. And what I'm going to say is I don't even care what the height of this is. Let's look at the radius of the Earth in meters. I'm actually going to go a little bit more accurate. The radius of the Earth in meters would be 6, instead of 6.4, it's like 6.38. So, and then, so it times 10 to the 6, okay, we have an extra 0 in here. So this is the radius of the Earth. Now, the distance from our mass to the center of the Earth would be the radius of the Earth plus its height above the ground. So let's say I hold this 1 meter above the ground. Do we need to put a 1 here? Of course not. Because remember, these values aren't really zeros, they're just placeholders. Again, in order to get anything happening here, we'd have to know, like even if we go a kilometer above the ground, that would be like replacing this 0, which is a 1, or that would be like adding a 1 to whatever this number actually is. So even if we're a kilometer above the ground, it's unlikely to have any effect. You could go to the top of Mount Everest, which is about 9 kilometers above the ground, and that might change a 6.38 to a 6.39. And again, we normally round off to 6.4 anyways. So again, as long as we're anywhere near the surface of the Earth, and that would include being on top of Mount Everest, that's our value that we would plug in here. So height above the ground is totally irrelevant. Even like a plane flying, they fly at about the height of Mount Everest. So typically planes flying, they're close enough to the Earth that it wouldn't even really be a rounding error to take the height into account. So that's one simplification. Whatever the height above the ground is, unless you're like going to launch something in a rocket that goes way above the surface of the Earth, above where even most planes fly, gravity is the radius. We can just plug the radius of the Earth into that equation. But now we still need to know all this other stuff. So let's say we have an object here. Like say this is the Earth. That's the ground. And let's say we have a mass here, and we know that the Earth is going to be pulling on that. That's a force of gravity. And in this case, the force of gravity would be big G times the mass of the Earth times this mass whatever that object is, and then divided by the radius of the Earth squared. So again, simplified it by ignoring that h because it's not even a rounding error. But so again, we've got to plug in g, me, and ra squared, and we do this all the time. So what we're going to do, let's just do this calculation once. We're going to do this. So let's just do this calculation one time and write down that number, whatever it happens to be. And then the force of gravity is just going to be the mass of whatever object that is times this thing, which we're going to calculate just once. I'm going to write this off to the side because I might need some room on the board. Okay, we're going to calculate that. So let's do that. We have 6.67. Now times 10 to the minus 11. I like positive exponents, so I'm just going to write that on the bottom. And we have newtons, meters squared over kilograms squared. So that's G. Then the mass of the Earth is around 6 times 10 to the 24th power kilograms. Going to write it like that. And then divided by the radius squared, which is 6.4 times 10 to the 6 meters. And we have to square that. So again, I mentioned that the radius of the Earth, more accurately, is 6.38. We're just going to do a fairly rough calculation here. And mainly because I don't know what the mass of the Earth is. I think I do remember it's like 5.98. And yeah, maybe we can go to a couple significant figures here. So let's give this a go. So first thing we want to do is clear this up a little bit. Let's go back to Newton's second law, F equals ma. Now we know that forces are measured in newtons. Those are the basic SI units. So a newton is equal to a mass, which is in kilograms, times acceleration, which is meters per second squared. So a newton is a kilogram meter per second squared. And we can write this way. A newton times a second squared is a kilogram times a meter. So I'm going to write this here. This conversion factor here, a kilogram times a meter is a newton times a second squared. So let's first look at the units now. And let's just go across the top and then the bottom. So here we have newtons times meters. Well, meters squared, so I'm going to write that meter times a meter times a kilogram, and then times a kilogram and another meter. Now on the bottom we have kilograms squared. That'll take care of that. Here we have meters squared because it's, this whole thing is squared. So, and then we have a newton, and then second squared I'm just going to write here. So all this stuff cancels out. And the units we get out of this are meters per second squared. So we know the units. Now let's look at the numbers. So we have G ME over RE squared. So this would be 6.67 times 5.98. Let me write this down first and then explain it a little bit. I'm just writing down the numbers that aren't like 10 to some power. So we have 6.67, 5.98. Here's 6.38 squared. And now let's look at the exponent. We have 10 to the 24th on top. On the bottom, here's 10 to the 11th. And here we have 10 to the 6th squared, which is 10 to the 12th. And remember, if you do like, say, 10 to the 11th times 10 to the 12th, that's 10 to the 23rd power. Right? You have the same base and you multiply them, you add the exponents. So yeah, here we have 10 to the 11, over here we have 10 to the 12. And so we can clean this up a little more. 10 to the 24th over 10 to the 23rd is just 10. So what we have is 6.67 times 5.98 times 10 divided by 6.38 squared. And that would be in meters per second squared. So let's see what we get doing this calculation. So on top, I'm getting 398.866. And what I'm going to do is I'm going to divide by 6.38 and hit enter, and then do it again. And here's the result I'm getting from this calculation. 9.7991 meters per second squared. Or if we round that off, what we get is 9.8 meters per second squared, which is little g. And so now if we want to know the force of gravity acting on an object, if we're near the surface of the Earth, and again, that applies pretty much anywhere even close to the surface of the Earth, the force of gravity is just mg. So like here, I erased it, if we have a mass of 10 kilograms, like say I'm holding an object that has a mass of 10 kilograms. This is not quite 10 kilograms. But let's say this is. Instead of having to plug all this stuff in to find the force of gravity, instead of needing to know the mass of the Earth and the size of the Earth and this gravitational constant g, I can just say 10 kilograms times 9.8 meters per second squared. The force of gravity is just 98 newtons. And again, this applies on the surface of the Earth. If you wanted to calculate, say, the force of attraction between the Earth and the Moon, you definitely can't just plug the mass of the Moon and multiply by g. That wouldn't even be close to the right answer. You'd have to use this equation for, like anything like astronomy related, you would use that equation. Or not on the Earth. Like if you were on Mars, you could do the same thing for Mars. You could define g for Mars, which would be big G, times the mass of Mars divided by the radius of Mars squared. You'd get a different value for g, but then the force of gravity would just be mg like before. So like you can think of g as being specific to any particular planet. Okay, so that's the force of gravity. And this is the only fundamental force that we're talking about. So we spent about 45 minutes talking about this so far, focusing primarily on gravity. And all we have left is all the other forces that we can deal with in this class. So I think what I'll do is I'm going to pause here and maybe just do that in a separate video. So, here. This one was just gravity, basically. And then I'll talk about other forces that we're going to come across in this class in a separate video.